Hello, I am Rafał Mantiuk. I am a reader at the University of Cambridge, and I would like to tell you about our new method to adapt any existing video quality metric to work with high dynamic range content. This is the work that was done with Maryam Azimi, who was a postdoctoral researcher in my group, and the work was funded by ERC, EPSRC, and also Canadian NSERC. The main problem of estimating quality of HDR content is that the visibility of distortions heavily depends on the absolute luminance of that content. And let me show you an example. I generated 4 test images, each one with different background luma. Then I added to each the same amplitude of noise in the luma space, so that the PSNR values computed on luma values were exactly the same. However, when you look at those patterns, I would argue that the visibility of the noise is not the same. It obviously depends on your display, but on my display, I would argue that the noise for the darkest background is less visible than for the 2 gray backgrounds. But perhaps we should not compute PSNR on luma values, but instead on linear absolute luminance values in units of candela per square meter or in nits. We can convert luma values into the amount of light emitted from the display using a display model such as gain gamma offset or GOG. GOG is a simple model that accounts for the gamma of the display, for the black level, its peak luminance, and in practice GOG model is well suited for most of the displays. So I use GOG model to convert each noisy rectangle to luminance and computed PSNR values. And the predictions are even worse. If you compare the 2 rectangles on the right and dB values, you can see more than 10 dB difference between them, which is huge. However, I would argue that the noise is comparable or even less visible in the brighter rectangle. The predictions are horrendous because physical linear luminance values, which are often used to represent HDR images, are strongly perceptually non-uniform. We should never ever compute quality in linear color spaces, but this is something that I unfortunately still often find in many papers. Instead, we should compute quality in perceptually uniform spaces, and in 2008 we proposed a very simple solution for that. We transform physical luminance into perceptually uniform units, which we then pass to the quality metric. And the metric could be PSNR, SSIM, or any existing metric. When we apply PU encoding to our toy problem, we see that dB values are much more similar and are a bit higher for the lowest and highest luminance because noise indeed is a bit less visible in those 2 cases. There are 2 use cases for PU encoding, and I need to explain both of them to provide context for our work. In the first use case, we evaluate the quality of HDR images. We start with test and reference images, which we need to tone map for an HDR display. There's sometimes a misunderstanding that HDR displays do not require any tone mapping, but in practice the display could not be bright enough to reproduce the content, and we need some form of tone mapping. Once we have linear color values, which correspond to the light emitted from a display, we can apply PU encoding and compute the quality using any existing metric. In the second use case, we can use PU encoding with standard display-referred images. In that case, we want any metric to account for the brightness of a display. The fact that distortions are going to be more visible on a bright than on a dark display. In this case, we use a display model such as GOG, which I explained before, to model the light emitted from a display. Then we pass the linear color values to the PU encoding and compute quality as before. This will remake PSNR into a metric that adapts to the brightness of a display. To explain our new work, I need to first explain in a single slide how perceptual uniform encoding is generally derived. The derivation is very simple and actually applicable to many problems. We want to transform a physical luminance shown on the x-axis into an abstract response of the visual system on the y-axis in such a way that the response increases by 1 unit when luminance increases by the detection threshold. What is the detection threshold? This is the smallest difference in luminance that is detectable by the human eye. What is important to note is that this detection threshold is not constant, but it varies significantly across the luminance. If we put our condition into an equation, we have that the derivative of our unknown response function is equal 1 over the detection threshold. And this kind of differential equation can be easily solved by numerical integration, also known as Fechnerian integration. This derivation is nothing new. It was first proposed in psychophysics by Fechner in late 1800, then reinvented in the decom grayscale function, then reinvented by us for coding HDR content images in 2004, improved in 2006, and then finally reinvented again by Dolby in 2013, and is known as a PQ function widely used for coding of HDR content. The derivation of all those is essentially the same, and the only thing that is different is the model used to compute the thresholds or delta L value. So what is new and different in PU21? There are 3 main improvements. First, we use the latest contrast sensitivity function measured up to 10,000 candela per square meter and therefore suitable for HDR content. Second, we derive thresholds for color banding, which is relevant for compression, rather than for Gabor patches, which are less relevant. And finally, we account for the effect of glare on our ability to see any coding artifacts. Let me now explain the first point. To derive any PU function, we need to know detection thresholds. And those are typically modeled by a contrast sensitivity function or the CSF. The CSF tells us what is the smallest detectable contrast. By convention, it predicts sensitivity, symbol S, which is the inverse of the threshold contrast. And the threshold contrast gives us the detection threshold, which we need for the derivation of PU encoding. CSF is a function of luminance, spatial frequency, size, and many other parameters. So one of the problems we need to solve when using CSF for the PU encoding is how to reduce all those parameters to 1 so that it becomes a function of luminance. On the right, you can see well-known Campbell and Robson chart, which nicely shows how small contrast disappears in our eyes, and the threshold at which it disappears differs across spatial frequencies. The CSF we use comes from our own work, in which we measured the detection threshold across a wide range of luminance, up to 10,000 candela. And for that, we use our custom-built HDR display with a rather high peak of 35,000 candela per square meter. We also put a lot of effort to make the display well calibrated and possibly color accurate. Here you can see the comparison of our CSF with that of Barton for the same parameters. And Barton CSF is the one that was used to derive the PQ function. It's easy to note that both CSFs are substantially different. The problem with Barton CSF is that it has never been fitted to the data for very high luminance levels. The second important improvement of PU21 is that we use the thresholds for banding rather than for Gabors. The banding artifacts are caused by the quantization to lower bit depth, and they reveal themselves as false contours or bands. This is why we'll call them banding or contouring artifacts. I would argue that banding is one of the most dominant artifacts in compression. At least this is the one that I noticed the most when watching Netflix. The model of banding detection, which we propose in HVEI paper, can tell us when the banding is visible to our eyes. Given a background color in LMS space, it predicts visual difference energy, which we can then use to find the probability of detection. The basic idea behind the model is that the quantization or error corresponds to the sawtooth pattern, which has analytical Fourier transform. We use the Fourier components of that error signal and the CSF to predict the visibility of banding. In all previous PU functions, the thresholds used for the derivation are assumed to be the peaks of the CSF, shown over here as black circles. This unfortunately means that we are effectively predicting thresholds for a Gabor patch of certain frequency like this one. The problem with this is that coding and other artifacts do not really look like Gabor patches. Our banding model predicts the thresholds based on series of frequencies, and it does it for banding, which is much more important and representative for compression artifacts. The final improvement that we account for is the effect of glare. By glare, I mean the reduction of a physical contrast by both the ambient light that is reflected from a display, but also the bright content that is on the display and is scattered in our eyes. The reduction of contrast is purely a physical effect. Let's define our contrast as the difference between two luminance levels divided by the lower luminance. When the glare is present, both L1 and L2 are elevated. But because we have the difference between L1 and L2 in the denominator, it means that the glare is added to the denominator, reducing the physical contrast. In our derivation, we made a simplifying assumption that the amount of glare is constant across the entire screen. Here I'm plotting contrast detection thresholds as the function of luminance for all combinations of our improvements. So first, using peaks versus banding model, you can note that the threshold function is much shallower and less conservative when we use banding model. Second, we account for the glare, or we don't, and the thresholds are much higher at low luminance when we account for glare. On the right, you can see all derived PU functions that we use in our comparison together with the old PU and also PQ. We use all variants of PU functions shown on the previous slide to predict image quality for our UPIC dataset. UPIC dataset is another work from our group in which we combine together two HDR and two SDR datasets and scaled them in the same quality units. The combined dataset has over 4,000 images. However, we use only the HDR portion in our evaluation. We compute image quality using the combination of each of those PU functions with PSNR, VSI, FSIM, SSIM, and multiscale SSIM. Then we measured correlation between the metric predictions and the subjective quality scores, which are shown in the plot on the right. The closer is the coefficient to 1, the more accurate is the metric. The plots clearly show that the combination of our two main improvements, the banding model and the glare adaptive PU, gives the most accurate quality predictions for this dataset. In summary, we propose a new perceptual encoding that is based on new high dynamic range contrast sensitivity function that models the visibility of banding artifacts rather than of Gabor patches, and that accounts for glare. We made the code available under the link on the slide. And because we fitted parametric function, PU21 encoding is very easy to port to any programming language. We hope that new PU encoding will help in the quality evaluation of HDR content. With that, I would like to thank you for listening.